The FOM method, or the full orthogonalization method, will be viewed as a convenient variation of GMRES. So let's first recall the definition of GMRES. I inserted here the parameterization of the Krylov subspace in terms of the QM matrix. And here we're going to use now that this is a linear least squares problem, and that will lead to a property. So we're going to use here that this linear least squares problem, which in turn implies that the normal equations are satisfied. The normal equations are formed by taking the system matrix and transposing it, and so we have this is, and here we have an equality. Okay, let's move this over to the left-hand side, and then we get the system matrix, and here's the system matrix times Z minus B. Okay, but this is in fact just the residual that we have in GMRES, which we started with here. So this means that the residual times this matrix is equal to 0. The fact that this equation is satisfied is the same thing as saying that the residual is orthogonal to this this subspace corresponding to this, and this is in fact A times the Krylov subspace, because A comes from there and QM is an orthogonal basis of a Krylov subspace. Now you may ask, why do we have an A here? And this question is actually the step that leads to the FOM method. So now we're going to do the same thing as in GMRES, but instead of imposing a orthogonality condition on A times the Krylov subspace, we will have orthogonality directly with respect to the Krylov subspace. This orthogonality can also be written in this form here, since QM is an orthogonal basis of a Krylov subspace. Now we're going to expand this in the same way that we used Rm up here. First we use this formula, which just comes from the fact that we assume that X lies in a Krylov subspace, and now we use that QM is generated from an Arnoldi method, which means that it satisfies the Arnoldi factorization, and we get QM transpose QM plus 1 HM bar Z minus EM. Okay, and that's all equal to 0. And now let's look a little bit closer at this matrix and see what that leads to. Due to the orthogonality of the Krylov subspace, we have that QM transpose QM transpose plus 1 leads to this matrix, identity and a 0 column. And if we multiply the HM matrix with the identity 0 matrix, we get exactly HM. So now we have an equality here. So we have 0 is equal to HM Z minus E1 normal B. By just solving that equation, we obtain that Z is equal to HM inverse E1 times normal B. HM is a square matrix. So FOM gives you directly as a Z vector by solving a linear equation. So HM is a square matrix, so in general the inverse exists. You can compare this with HM, where we, in order to get the Z, we solved a linear least squares problem. To get FOM implementation given a GMRES implementation, you only have to change one line of code, and that is to replace how we compute the Z vector. And since the backslash operator solves the linear least squares problem and also a linear system, the code will only be modified in a very subtle way.